Welcome to Unit 1, Lesson 2. We're going to talk about the parent graphs of trig functions. What do I mean by parent graph? Well, you've learned about quadratics in the past. And if we look at a quadratic where it is not vertically stretched or vertically shrunk, and it has a vertex at the origin, that's considered the parent graph. It hasn't moved up, it hasn't moved down, it hasn't moved left or right, there's no stretch or shrink. We just talk about its basic graph, and that's what this video is about. We're going to talk about the parent graphs of sine, cosine, and tangent, cosecant, secant, and cotangent in this video. All right, so let's first talk about y equals the sine of x. I have an applet to show you. This link is in your Schoology page so that you can do this yourself. But here's what I like. Every single parent graph is derived from the unit circle, and we unwrap it. So what you see on the left side of your screen is a unit circle. And we calculate what the sine is at 0. The sine of 0 is 0. The sine of pi over 2 is 1. The sine of pi is back to 0. The sine of 3 pi over 2 is at negative 1. So you're going to see that this applet is going to take more angles. Right now we're just looking at 0, pi over 2, pi, 3 pi over 2, but we have all of those angles in between. So let me start. And hopefully you can see through this visual, the first half of the unit circle gets us to pi, each quadrant gets us a quarter way through, and we end with one complete rotation of the unit circle at 2 pi. So that's why we say that the sine is 2 pi periodic. It takes 2 pi radians for us to get through one complete cycle of the sine curve. Obviously this keeps going and it's color coded so you can see how each of them correspond. I encourage you to spend some time on your own kind of looking at that if this interests you. Also, I want to state that if this is not the first time you've talked about the graph of a sine of x, there's all different kinds of ways to teach this from a table. And if you noticed from that applet, we tend to have our highs and lows and where we hit the midline at those quadrants. So usually I pick x values that are 0, pi over 2, pi, 3 pi over 2, and 2 pi. Why do I pick those? Because all of the ones in the middle are irrelevant, but they don't give us a high or a low or a midline value. So this is where you have to know your exact values. The sine of 0 is 0. The sine of pi over 2, the y value at pi over 2 is 1. The y value at pi is back to 0. The y value at 3 pi over 2 is negative 1. And the y value at 2 pi is back to 0. So when we plot those, here's 0, 0. We have pi over 2, 1. Pi 0. 3 pi over 2, negative 1. And back to 2 pi. It is a curve, so it should flow. It should not have sharp turns in the graph. If you wanted to complete a second period of this, then we can just follow the pattern. This is going to go back down, back to the midline, back up, and that would be 2 periods. So let's talk about some vocabulary. The amplitude of a graph is how high or how low the graph goes from the midline. Generally speaking, the amplitude is only going to apply to the sine and the cosine, but we are going to use it as a term. But in this case, if we look at the distance from the midline to the maximum or the minimum, that is 1. The period, how long did it take us to get through one cycle? It took us 2 pi radians. Now we need to consider the domain and the range. All right, so sometimes this is why I teach with the T-chart. I just arbitrarily picked 0, pi over 2, pi, 3 pi over 2, and 2 pi because that's the first rotation of the unit circle. But we could have picked pi over 4, and the sine of pi over 4 is root 2 over 2, and so this point right here would probably represent that. We could have picked, 2 pi over 3. We could have picked negative 17 pi over 25. We're not limited to what x values we can pick. So the domain of the sine curve is going to be all real numbers. I use that symbol. You can also write it out in English words. All real numbers. But for the purposes, most kids will just write, it's like writing an R with a parallel sign. We do have a range restriction, however. When we talk about the range is all the possible y values that will be output when we pick an angle. Well, I just, again, arbitrarily chose 5 points, but this obviously does keep going on forever and ever and ever. And so if I said, is there a range value that's 2? As the parent graph only, I'm not talking about translated sine graphs, but the parent graph, you're never going to get higher than 1 and you're never going to get lower than -1. So we can say that the range, if you want to use interval notation, is from -1 to 1 inclusive, because I can actually have a range value that is 1 or -1. If you want to use, and I encourage you to use interval notation, if you want to use inequality notation, your y values are between -1 and 1. So what's your takeaway from this? I would make sure, I will teach transformations in the next video based on this table feature. So you want to make sure you have in your notes that this is the table that we will use for the sine curve. I kind of over-explained the sine. When we do the next 6, I won't over-explain them as much, but I'm going to follow the same process. We're going to make a table. We're going to plot our points. We're going to talk about the amplitude, period, domain, and range. Okay, let's talk about the cosine. All right, so we're going to start with the table. Again, if you have prerequisite knowledge and you don't want to do the table, I'm just letting you know I have found from a lot of students that the table is very helpful when we start translating advanced trig graphs. That's just the feedback students have given me in the past. All right, so we have x cosine x. We're going to do the exact same thing with cosine. Let's talk about what's happening on the unit circle. Let's talk about what is happening at those quadrantal angles. So 0, pi over 2 pi, 3 pi over 2, and 2 pi are going to be the angles I'm going to use to do my parent graph. Well, now we look at the x values. The x value at 0 is 1. The x value at pi over 2 is 0. The x value at pi is back at 1. Excuse me, -1. 3 pi over 2 is at 0, and we're back to 1 at 2 pi. So let's go plot. So I'm at 0, 1. Pi over 2, 0, pi -1, back to 0, back to 1. This is not a V. If you draw a V, that's an absolute value. It is a curve. And again, if you want to extend the pattern to make a second period, you would just follow the pattern. So notice that if I can try to pinch here, if you look at both of those side by side, they both are, these are called sinusoidal graphs. Sinusoidal, I'm terrible at the spelling here. Sinusoidal. Sinusoidal graphs. Why? Because they both follow this like up, down, like a wave. The difference is you've got sine starting at 0, but cosine starts up at 1. That is going to be their main difference. And if you shift either of them over pi over 2 radians, that's why they're going to be called cofunctions, that you would have the same graph. Okay, let's talk about its amplitude. Again, the amplitude is, if you think about this as the midline, let me get a different color. If you think of this as the midline, how high and how low does it go from the midline? It's a unit of 1, again, on the parent graph. We're going to stretch these or shrink these out in the next lesson. If you notice the purple or just the red, we got through one complete cosine curve in 2 pi radians. The domain is going to be similar. Again, I chose these arbitrarily, but I could have picked pi over 4. I could have picked 75 pi over 22. I could have picked any negative value. Your x values, you will always have an x value on the cosine. And similar to the range of sine, we can only have range values that are between -1 and 1. All right, let's go to tangent. This is where it starts to get a little bit more complicated. Why? Well, let's think of the unit circle. When I think of the unit circle, and I've got a point here that is 1, 0, this is the point 0, 1, this is the point -1, 0, the point 0, -1, your tangent isn't just an x or y value. Your tangent is the y over x value. So the tangent at 0 is 0, but the tangent at 0, 1 is undefined, as is at 3 pi over 2. So we have places in the graph, so tangent's going to be different, where we are going to have what's called asymptotic behavior or asymptotes. And you should be familiar with asymptotes when you looked at rational functions, exponential functions, or logarithmic functions in Algebra 2. All right, so let's get rid of this and let's do our table. Actually, let me undo that. Let me explain why I'm going to pick the values in my table. Tangent, we're going to explore in just a minute, is not going to have a period of 2 pi. It's only going to be pi radians. I'll be able to get through one complete period or cycle of the tangent curve in between asymptotes. And again, it really is arbitrary what you pick, but most mathematicians in most books, they pick from negative pi over 2. So instead of calling this 3 pi over 2, they call negative pi over 2 to pi over 2. They define that as the quote-unquote parent graph. So let me keep that up. Here's what I'm going to do. So I have x tan x, and I'm going to start with negative pi over 2 because that is going to be an asymptote. That's going to be undefined. And I'm going to end with a positive pi over 2 because my tangent is undefined there as well. I'm going to pick 0, obviously, in the middle because makes it symmetric. But unfortunately, if I only graph that much, if I put an asymptote, so my expectation is that you will use a dotted vertical line for your asymptotes so that we can communicate that you know what's going on there. I know on a graphing calculator, they leave these blank. I don't want blank if you want full credit. I need evidence that you understand where the asymptote is at, so I do expect some sort of dotted line. So if you just put a dot at 0, 0, that doesn't give me enough information. I don't know what's going on. So we need to pick a suitable value that is in this fourth quadrant and think about what tangent value is easy to calculate. Well, I think it's negative pi over 4 because at all of the pi over 4 reference angles, those are all root 2 over 2, root 2 over 2. And so the same thing over itself is 1, but since I'm in the fourth quadrant, your tangent is negative 1. And if I pick a positive pi over 4, the tangent is 1. So in every single graph, you are always going to have to give me 5. This is what I call the main 5 points of the graph. So at negative pi over 4 and positive pi over 4, I've got negative 1 and 1. And so the graph has that shape. It looks very similar to x to the third. It kind of has that similar shape, but the points on it are not polynomial in nature. But I just wanted to give you a frame of reference for what that looks like. And if we were going to continue this graph, you would think about what's happening at pi over 2. We have our asymptote. The tangent at pi is also 0. The tangent then if we were going this direction, would be at 3 pi over 2. So we have another asymptote. And the pattern is just going to continue. So let's answer our questions. What is the amplitude? Friends, there is technically not an amplitude because there isn't a distance, but we will have vertical stretches and shrinks. So we will discuss how the number in front is the amplitude or vertical shrink or vertical stretch. This should be familiar to you. Think about when you did graphs like y equals 1/2 x squared. It made the graph of x squared flatten out, right? You had a vertical shrink. So we still have that, but in Trig, they give amplitude a special name. So our amplitude in this graph is 1. Some kids refer to it as a vertical stretch. That's fine as well. Big change, the period is pi. The period is not 2 pi like it was for sine and cosine. Domain and range. All right? Notice how the shape of the graph is going to go up forever and down forever. That's affecting y values. So in this case, my range is all real numbers, but what I have is a domain restriction. So how do we talk about that domain restriction? All right, this is how I have been successful with kids. Again, this is not the only way to do it. When I have my domain, I have all real numbers. All right, what can't x be? X can't be negative pi over 2, pi over 2, 3 pi over 2, and think about what the distance is between those. The distance is at every pi radian. after pi over 2 or 3 pi over 2, we have an asymptote. So this is how I choose to write it. Pick an asymptote. I tend to pick the first positive one. You don't have to. It's pi over 2. And we need to add pi n, where n is an element of the integers. Z is a symbol for integers. You can write out the word integers. And sometimes I allow kids to just write n is an element of the integers at the top of their paper, so you don't have to write it on every single question. I get it. But this is a general statement to discuss that all of the asymptotes occur on basically all of the odd multiples of pi over 2. So there's your tangent. Kind of a hot mess, but let's move on. It gets even messier. So now let's move on to our reciprocals, and I want to show you 2 different approaches to how to do the cosecant. And I don't have a preference, it's how your brain works. All right. We know that the cosecant is the reciprocal of the sine of x. So if I look at this from a table perspective, I have x cosecant x. All right, let me think of it this way. I'm going to start with how I started the table for sine. 0, pi over 2 pi, 3 pi over 2, 2 pi. And in the sine curve, we have, it starts at 0, it goes up to 1, comes back to 0, goes down to -1 and 0. But since this is the cosecant, I have to take the reciprocals. So that means that becomes undefined. So cosecant's going to have 3 asymptotes in its parent graph. The reciprocal of 1 is still 1, and the reciprocal of -1 is still -1. So kids go, okay, Nap, I've got this. All right, I'm going to put my asymptote on the y-axis. I've got another one at pi. I've got another one at 2 pi. And then I'm going to plot these points, and that's not enough information to see what's going on. I'm still going to stand by the fact that this is what I'm going to use in future lessons for my 5 points, but let's think about this. Think about what's happening at pi over 4. No, actually, pi over 4, let's think about what's happening at pi over 6. I picked pi over 6 because the sine of pi over 6 is 1/2, so its reciprocal is 2, correct? So at pi over 6, I would be at 2. Well, let's talk about what's happening at 5 pi over 6. At 5 pi over 6, the sine of 5 pi over 6 is 1/2, so its reciprocal is also 2. So using that as an example, what you do is, again, they're not parabolas, but you do get a U shape. And again, why did I arbitrarily pick pi over 6? Because 1/2 is easy to reciprocate. If I have 2 over root 2 and reciprocate it, you can, but it's not, you don't get a nice even integer to plot. All right, so let's stay on with this. If I think between pi over 2 and 3 pi over 2, if I consider what's happening at 7 pi over 6, the sine of that is -1/2, so I would reciprocate that. It would be a -2. And then at 11 pi over 6, that would also be a -1/2 in terms of its sine value, and if I reciprocate that, I get a -2. And again, I get that U shape. Okay, that is one way to go about it. Here is a second way that you can go about it. Now that you understand that you're going to get this U shape for the cosecant, what some kids do is I'll do it in gray, think of that kind of like a pencil. They go ahead and they plot the sine curve. And some kids don't even connect them, they just leave the points. And what you have to realize is that your midline, those are your 0 values, that's where you get your asymptotes. And then they know to draw their U's at the points. So again, some people draw in their cosine first, then they know to make asymptotes on their midline and draw their U's. Keeping in mind, though, that the actual graph of the cosecant does not contain the cosine. This is the actual graph of your cosecant. So again, amplitude, vertical stretch. Well, if you think we haven't done anything, this is the parent graph, so your amplitude, it's going to be 1 in all of our parent graphs. And we'll explore more of what that means in future lessons when maybe that point, like at this point right here, maybe that was more at 2. The period is similar to your sine curve. It's 2 pi. We do have both domain and range restrictions, so let's talk about that. So my domain restrictions, I have asymptotes at 0, at pi, at 2 pi, and that distance in between them is pi. So I say my domain is all real numbers. That kind of covers everything between, except x cannot be, well, I can pick 0. That's my first one, plus pi n. Some people will just write that as pi n. And as a reminder, n is going to be a member of the integers. I'm going to be a hair lazy and just... well, maybe I shouldn't be lazy. We're on a video. Just as a reminder that n is going to be an element of the integers. All right, now let's talk about range. When I talk about range, you have this area. This area in here does not have any y values associated with it. But I have y values from negative infinity all the way up and starting at 1 all the way up to infinity. So those are two separate intervals. So unfortunately, you cannot write one statement to talk about them both. My range is going to be from negative infinity. And when using interval notation, that always gets parentheses because we can't physically hold infinity, through negative 1 inclusive because we do have a point here at negative 1. And then union 1 to infinity. If you want to write this using inequality notation, it would be negative infinity is less than negative 1, is less than or equal to x. Sorry, is less than x, is less than or equal to negative 1. And then you would also have 1 is less than x, is less than or equal to x is less than infinity. All right, two more. We're going to approach secant very similarly. I'm going to give you a t-chart, and then you can do the same thing. Since secant has a reciprocal of the cosine, some kids will plot the cosine and then put in their asymptotes and their u's appropriately. So here we go. So I have x, secant of x. How am I going to think of this? Let's start out like the cosine curve. 0, pi over 2, pi, 3 pi over 2, 2 pi. We know that the cosine starts at 1, comes down to 0, down to negative 1, back up to 0, back up to 1. But since this is the secant, we have to take their reciprocals. So at 0, I'm at 1. And then at pi over 2, I have an asymptote. I'm at negative 1 at pi. Asymptote at 3 pi over 2, and at 2 pi I am back to 1. Since we're talking about cosine, the cosine of 60 degrees or pi over 3 is 1/2. So if I reciprocate that, that would be a 2. So pi over 3 is right here. So we know that we're going up in that direction. If you consider in the second quadrant 2 pi over 3, my cosine is going to be a negative 1/2, so when I reciprocate that, it's at negative 2. At 4 pi over 3, the cosine is also negative 1/2, and if I reciprocate that, we get negative 2, so that's where I get my other U shape. And then at 5 pi over 3, cosine is positive in the fourth quadrant, so when I reciprocate 1/2, I get a positive 2. And that is one complete cycle of the secant curve. So again, what do some students do? Some students will go ahead and they will draw the cosine curve. And that didn't curve out very well. I think that's a little technology mishap here. Let me see if I can do this a little bit more dotted. Nah, it doesn't like me right now. Does not like me right now. Well, you can see it a little bit better. The dotting is trying to make it. But nevertheless, you can see that you've got this cosine curve in there. What I just wrote in gray is not part of your graph, but that is a strategy where this is the midline. So it's hitting the midline at those two places. That's where my asymptotes go. And then I'm going to have U's drawn from those highs and those lows. So again, my amplitude or vertical stretch is 1. It takes me 2 pi radians to get through one complete cycle of the secant curve. We do have domain and range restrictions. If I think of the domain is going to be all real numbers except x cannot be, again, it's at pi over 2, at 3 pi over 2. You'd have another one at negative pi over 2 and at negative 3 pi over 2. So I pick pi over 2. The distance between asymptotes is pi n, and n is an element of the integers. Your range is in common with the cosecant graph. You have this area of range. I can have y values in both directions, but not in between. So my range in interval notation is going to be from, let's do an erase, it's going to be from negative infinity to negative 1 inclusive, and 1 inclusive to infinity. And let's wrap up cotangent. And I will let you know, on assessments, this is the graph that kids, either one, I can't tell you how many times kids give me a cosine graph, you just don't read. So don't do that. Make sure that you are reading, and I usually have 2 or 3 kids every year on a test give me a cosine graph instead of a cotangent graph. It's actually more common than you think. But cotangent, we can't approach cotangent like we did secant and cosecant. So cosecant and secant, we could really look at this from a sine cosine perspective because we were reciprocating. And you can do that with cotangent, but we're not going to graph the tangent first. And hopefully you see why momentarily. So I'm going to start again from a table. So we have x cotangent of x. Let's remind ourselves of the unit circle. All right, at 0, we have the point 1, 0. At pi over 2, we have the point 0, 1. At pi, we have the point negative 1, 0. And at 3 pi over 2, we're at 0, negative 1. The cotangent is x over y. So that means the cotangent at 0, that's undefined. The cotangent at pi over 2 is 1. Sorry, is 0, 0, 0, 0. The cotangent at pi is back to undefined, and I have a 0 cotangent. So on tangent, you had asymptotes at the pi over 2, 3 pi over 2s and their coterminal angles, but they're on the 0 pi for cotangent. So similar to tangent, we will get through one complete cycle or period of the cotangent graph in pi, but we're going to bookend them by asymptotes that are at 0 and pi. We'll pick a pi over 2 in the middle, and I'm going to take a pi over 4 and a 3 pi over 4 approach because at pi over 4, you have root 2 over 2, root 2 over 2, and it's easy for me to do an x over y value because they're the same and we get 1. So we are bookended by asymptotes. So at 0 and pi, we have asymptotes. At pi over 4, we know we have a cotangent of 1. Cotangent is negative in the second quadrant, so that would give us a negative 1. And the cotangent at pi over 2 is 0. So you're going to notice that the difference is cotangent is reflected over the x-axis. Tangent has a shape more like an x to the third graph. Cotangent has a shape that's more like a negative x to the third graph. So in general, for whatever reason, it usually is the cotangent graph or being asked tangent and cotangent on a similar assessment that you really have to keep track of those values. And if you ever get stuck, you can always go back to your unit circle and unwrap. All right, so let's finish up the questions. Again, it really isn't an amplitude so much as it a vertical stretch, and we don't have one, so we call it 1. I can get through in pi radians. Now, we have a domain restriction, but not a range restriction. My domain, again, is all real numbers, but x can't be 0 or pi or 2 pi or 3 pi, and the distance between them is pi. So x cannot be, I'm going to use 0 plus pi n. That was a sloppy. Let's redraw that. X cannot be 0 plus pi n or just pi n, where n is an element of the integers. But friends, your range, I don't have any place where I don't have a range. My range is all real numbers. And for the record, if a student ever gave me interval notation of negative infinity to infinity, that of course is correct as well. All right, so your assignment is to do the Trig parent graph worksheet and upload that, and enjoy working with Trig parent graphs.